In this we will study what is Laplace transform and its properties. The content which we are going to cover is Laplace and inverse Laplace transform, Laplace transform properties, Laplace transform theorems. So what is Laplace transform? So in the undergraduate curriculum you might be known there are three types of transform. First is your Laplace transform, Fourier transform and Z transform. In this we will cover the Laplace transform. In the last lecture you have seen the significance of Laplace transform in the control system. The Laplace transform is usually used in solving the continuous linear differential equations of the type encountered in the circuit theory and the systems. The advantage of using Laplace transform is that it makes the cumbersome differential equation algebraic and therefore the maths become simpler to handle. And in the end we can take the inverse and go back to the time domain. So the Laplace transform of a function f of t can be defined as Laplace of f of t is equal to capital F of s is equal to integral over 0 to infinity f of t into e raised to minus st dt, whereas the inverse Laplace transform is defined by Laplace inverse of f of s is equal to f of t 1 by 2 pi j integral over sigma minus j infinity to sigma plus j infinity f of s e raised to st into d of s. So we will see the Laplace transform of unit step signal. The Laplace transform of unit step signal can be given as, since the amplitude or magnitude of unit step signal is 1, from this we can get the Laplace transform of unit step signal as 1 by s by solving this in the Laplace transform equation. So the Laplace transform of unit step signal is 1 by s. Laplace transform of unit impulse. The Laplace transform of unit impulse signal is given as delta of t minus t0 is equal to 0 when t is not equal to 0, and it is equal to 1 when t is equal to 0. Here in this pictorial representation you can see the unit impulse signal. So the important property of unit impulse is a shifting or sampling property, which is integral over t1 to t2 f of t delta of t minus t0 dt is equal to f of t0 when t1 is smaller than t0 is smaller than t2, and 0 when t0 is smaller than t1 and t0 is greater than t2. In particular, when we let f of t is equal to delta t, we can take the Laplace transform as Laplace transform of delta of t is equal to integral over 0 to infinity delta of t e raised to minus st dt is equal to e raised to minus 0 of s is equal to 1. So some of the important properties of Laplace transform are, first is your linearity. Suppose consider two input signal x of t and y of t. The Laplace transform of the signal can be given as x of s and y of s. As in the previous lecture we have studied that linearity property obeys the principle of superposition. By using this superposition principle we can write Laplace transform of ax of t plus by of t is equal to a capital X of s plus b capital Y of s. Next property is time shifting property, which is Laplace transform of f of t minus a into u of t minus a is equal to integral over a to infinity f of t minus a into e raised to minus st. By solving the above equation we can get a transform pair as Laplace of f of t minus a u of t minus a is equal to e raised to a minus s f of s. Laplace transform next property is frequency shift property, which is Laplace transform of e raised to minus at f of t by solving the above equation using the standard Laplace transform definition. We can say a transform pair as Laplace of e raised to minus at f of t is equal to f of s plus a. So we'll see the example of frequency shift property. We will find the Laplace of e raised to minus at cos omega t. Since here f of t is equal to cos omega t and the Laplace of cos omega t is f of s is equal to s by s square plus omega square, and by using the frequency shift property we can write f of s plus a is equal to s plus a by s plus a square plus omega square. Therefore we will get a Laplace transform pair as Laplace of e raised to minus at cos omega t is equal to s plus a by s plus a square plus omega square. Here s plus a is because of frequency shift property. Next property is time integration property. Here Laplace of integral over 0 to infinity f of t dt can be represented by using time integration property, and by using integrate by parts theorem we can write the time integration property, and putting the substitutions and carrying out this integration will show that Laplace of integral over 0 to infinity f of t dt is equal to 1 by s integral over 0 to infinity f of t into e raised to minus st dt, which is equal to 1 by s f of s. So next Laplace transform property is time differentiation. If Laplace of f of t is equal to f of s, and here we want to show that Laplace of df of t by dt is equal to s f of s minus f of 0, which is the time differentiation property. So by using integrate by parts and substituting the following conditions we can solve this equation, and we will get Laplace of df by dt is equal to f of t e raised to minus st, where substituting integration over 0 to infinity minus integral over 0 to infinity f of t and integration of minus s e raised to minus st dt, we will by using solving the equation we will get Laplace of df of t by dt is equal to s f of s minus f of 0. Again we can extend the previous case. Here we can write Laplace of df of t square by dt square as s square f of s minus f of 0 minus f dash of 0. So in general we can write Laplace of df of t raised to n by dt raised to n is equal to s raised to n f of s minus s raised to n f of 0 minus s raised to n minus 2 f dash of 0, so on till minus f raised to n minus 1 into 0. So we'll see some of the another Laplace transform properties. Here the Laplace of e raised to minus at u of t can be given as Laplace of e raised to minus u of t is equal to 1 by s plus a. Another, the Laplace of tu of t can be given as tu of t is equal to 1 by s square. We can use the most recent property, that is t raised to n is equal to n factorial by s raised to n plus 1. Now we will see the Laplace of cos omega t, which you have earlier seen in the frequency shift example. Here we can write cos omega t as e raised to j omega t plus e raised to minus j omega t by 2. Thus substituting this in the Laplace transform definition we can get Laplace of cos omega t as s by s square plus omega square. So the Laplace transform pair can be given as cos omega t u of t is equal to s by s square plus omega square. So some of the important transform pairs are delta of t is equal to 1, u of t is equal to 1 by s, e raised to minus st is equal to 1 by s plus a, t is equal to 1 by s square, t raised to n is equal to n factorial by s raised to n plus 1, t e raised to minus at is equal to 1 by s plus a square, t raised to n e raised to minus at is equal to n factorial by s plus a raised to n plus 1, sin omega t is equal to omega upon s square plus omega square, cos omega t is equal to s by s square plus omega square, e raised to minus at sin omega t is equal to omega by s plus a square plus omega square, e raised to minus at cos omega t is equal to s plus a by s plus a square plus omega square, sin omega t plus theta is equal to s sin theta plus omega cos theta by s square plus omega square, cos omega t plus theta is equal to s into cos theta minus omega into sin theta by s square plus omega square. Another common transform properties are f of t minus t0 into u of t minus t0 for t0 greater than equal to 0 is e raised to minus t0s into f of s, f of t u of t minus t0, t is greater than equal to 0 is e raised to t minus t0s, Laplace of f of t plus t0, e raised to minus at, f of t is equal to f of s plus a, d raised to n f of t by dtn is s raised to n f of s minus s raised to n f of 0 minus s raised to n minus 2 f dash of 0, so on. Tf of t is minus df of s by ds, integral over 0 is to t f lambda into d lambda is equal to 1 by s f of s. So now we will look some of the famous Laplace transform theorems. First is your initial value theorems. If the function f of t and its first derivative are the Laplace transformable and f of t has the Laplace transform f of s and the limit s tends to infinity s of s exists, then we can write limit s tends to infinity s f of s is equal to limit t tends to 0 f of t, which is equal to f of 0, which is the initial value theorem. The utility of this theorem lies in not having to take the inverse of f of s in order to find out the initial conditions in the time domain. This is particularly useful in the circuits and the systems. So we'll see the example of initial value theorem. Here we are having function f of s as s plus 2 by s plus 1 square plus 5 square, and we need to find f of 0. Then we can write f of 0 is equal to limit s tends to 0 s into f of s according to the initial value theorem. By substituting the value of s tends to infinity, we can write output as 1, f of 0 is equal to 1. Next is final value theorem. Here, if the function f of t and its first derivative are the Laplace transformable and f of 2 has the Laplace transform f of s and limit s tends to infinity s f of s exist, then we can write limit s tends to 0 s f of s is equal to limit t tends to infinity f of t, which is equal to f of infinity, which is nothing but a final value theorem. Again, the utility of this theorem lies in not having to take the inverse of f of s in order to find out the final value of f of t in the time domain. This is particularly useful in the circuits and the systems. So example of final value theorem is, here again we are having a function f of s as s plus 2 square minus 3 square divided by s plus 2 square plus 3 square. Here note, f inverse of s is t e raised to minus 2t cos 3t, and we need to find f of infinity. So according to the final value theorem, we can write f of infinity as limit s tends to 0 s f of s, which is equal to limit s tends to 0 s into function f of s. And substituting the value of s, we will get f of infinity is equal to 0. Summary. So in this we have seen the Laplace transform representation, some of the important properties of Laplace transform, and examples of the Laplace transform. Thank you.